Last time we went over the energy accounting for molecular D2 to find out how the energy is generally dispersed in the covalent bond. Shown here is a depiction of the radial distribution of the deuterons due to the minimum energy we found. We now start to explore how the D2 star intermediate comes into being. We start again with two deuterons, but need to discern what new electron behavior can be found. We start by looking at scattering behavior of plane waves. Conduction band electrons can be characterized as waves which fall out of the block function solution to a periodic crystal. The scattering center with approaching waves is the classic quantum text depiction, usually showing the waves approaching, then the circular pattern leaving, as well as the original wave continuing on. In the video, we can show one wavefront moving through the scattering center. Now we place two scattering centers side by side, add a plane wave, and watch what happens. It doesn't take too much imagination to visualize an electron instead of a wave. Now we go back and take a look at our scattering deuterons and an approaching wave again, and draw a vector on the wave to represent the direction and velocity or momentum. It doesn't matter where we put this vector since the plane wave fills all space. So we put it in the center for convenience. We know the metals have electrons going every which way, so what happens when the wave doesn't align with the diffraction center? Well, these waves will interfere with themselves and not contribute to this stationary state. But we know that the deuterons should be orbiting, so we assign this new wave, number 2, to a new deuteron position. We can continue this for a complete orbit of the deuterons. We also know that the electrons represented by these waves come in energies from about 0 to the Fermi energy. This gives a full Fermi sphere of electron momentum states. This is commonly referred to as momentum space. In order to describe a diffraction scattering event such as this, the wave functions for the various particles must be found. In this case, we are looking for a time-independent or stationary wave function to describe the diffraction pattern. We start by noticing the oscillating electron behavior to be Newtonian, not necessarily quantum. Mathematically modeling the two deuterons and electron does indeed give a classical Newtonian bond of the deuterons by the electron. As we will see in a minute, this bond works non-classically too. At large deuteron separations, tunneling is required just like the covalent bond. We will find the electron has an average kinetic energy of about 12,000 electron volts. This means the electron must do about 12,000 electron volts of work to drop this deep into the deuteron potential well. The question is, how? We can answer this with a simple pendulum example. The swing pendulum puts all the kinetic energy into one dimension. Now, by deflecting the weight into the circular orbit using two dimensions, gives a higher overall kinetic energy. By letting the ball spin in the plane of the right angles to the pendulum, the average kinetic energy is even higher. To review the pendulum example then, we had an orbital with kinetic energy supplied by a given drop in height, then a three-dimensional motion with combined pendulum velocity and rotational velocity, giving a higher total kinetic energy and a commensurate lower potential energy. It's important to note that both situations started at the same potential. With this example in mind, we can now draw a caricature of the orbit in the D2 intermediate state. We'll find that the force felt by the electron near the z-axis is proportional to the distance away from the axis. This gives the parabolic potential. We'll see that this is critical to separately describing the motions of the electron and the commensurate kinetic energy in the three dimensions. This next picture shows a graph of the potential felt by the electron along the z-axis. The top is at 0 and the bottom of the scale is minus 12,000 electron volts. The electron spirals along this axis exposed to this widely varying potential. The next slide shows the same potential plus the wave function of the electron along the z-axis. The deuteron separation here is about 0.1 angstrom. Note, the electron must tunnel almost the entire 0.1 angstrom. The very high average kinetic energy of the electron allows for this. This next graph shows three planar slices through this same graph at 0, 0.02, and 0.04 angstrom from the center. The next graph then shows these slices with 0 as the potential on the z-axis. The potential is parabolic in x. This may be confusing, but it just shows the potential change moving away from the z-axis. So why is this important? Well, the parabolic potential gives rise to Gaussian wave functions for the x and y dimensions, which are completely independent of each other, thus two energies independent of z in the ground state. This is sort of akin to the angular and magnetic quantum numbers in chemistry. In fact, they originate from the same motion, orthogonal to the radial position vector of the deuterons. The z-axis of the electron is always aligned with the deuterons, so that any xy motion is like angular motion, but very local to the axis. The last slide gives rough numbers for the energy accounting in the D2 intermediate.